Well, thanks everyone for being here, and it's a pleasure and a real honor to be here, to be back in Frankfurt, and for this fantastic event. And today I'm going to focus my presentation on the domain of 3D printing, digital design. Not going to focus on my recent obsession with AI in design. So I'm going to more focusing on the Aero Lab, the architectural research lab that I founded in Singapore in 2016. So one of the motivations that we have to use 3D printing is, or to use digital manufacturing and digital design, is that we have a problem with construction waste, and that happens every year. And we believe that the use of technology, and especially additive manufacturing, can contribute to lower the levels of energy in production, to optimize the construction, and to explore different ways and novel ways to contribute positively to our environment. So in our lab, we pose research questions to solve critical problems and improve our built environment. So one of them was a question that we had from a logistics company, DB Schenker, reached us to my lab with a question. It's like, we have a lot of waste here every year. I want to do something with it. So can we do something with packaging waste? So we started thinking of what could be possible to do, right? And then we started working with these ideas that basically started from a very unusual brief. This is basically what we got. We have cardboard, we have plastic, we have bottles, foam, and basically it's like, well, figure out. Let's imagine something with this waste. So these are our raw materials. So the pallets, bottles, foam, cardboard, and then we started thinking of processes to work these basically materials that we had to process them. And some of them are working with technologies that are already there for quite some time, and we found creative ways to basically to collect the waste. Basically, we went to their place to collect the waste. We did the Zoom cutter for the sections, and then we designed chairs for the cardboard tables. We collected them, and then we started working with simple algorithm that creates a shape, and internally we created a structure that basically holds the weight and creates this kind of prototypes. So we made a number of them. Also with the pallets, we created like a nested geometry that created large-scale tables for dining space that they had. So we did like some nesting algorithms with the grasshopper, simple ones with our students, and tested the integrity of the table, and that was the result. And we look at basically 3D printing of the main features here. So we got a lot of plastic bottles. So the idea was to upcycle them into large-scale chandeliers. And we developed two strategies. This was part of a research grant that we had with NAMIC, which is the National Additive Manufacturing Institute in Singapore. And then we started working with geometry that could be printed in our standard 3D printers using PET. And the other one was working with robotic printing. So we work with our unit, our robotic arm that allows us to print large-scale structures and to explore the expressive way to turn this plastic into appealing designs. The idea is that we're using waste here, and we want to make it appealing. We are used to seeing like really designs coming from waste that are not connecting to people, and the idea was to use design geometry to connect with the user. So you can see here the results. This is the prototype that we were working with. Our researcher printing one of these panels is about 1.5 meters tall. It's a bit 25 kilos of plastic upcycled here per piece. So we print them in this fashion. We created this panel that has structural stability, and we connected it in this way, right? So here where you can see 150 kilos of plastic fully upcycled here in this chandelier feature. So this is kind of the central chandelier, and behind in the red wall we start displaying the processes. So this was supposed to be the dining space for the employees, and we turn it into kind of a more of a space in which people can learn about these processes. So we created this central chandelier, and we also created a number of them on the tables. So this is a feature that integrates 440 individual tiles, and those tiles are created fully with parametric design, setting the connection detail for each of the tiles. In the end, we have, I think it's 9 different tiles, because they connect, it's a rip of 9 tiles, and they readily integrate. And also here, we're looking at detailing, right? Working with 3D printing, we can integrate profiles, we can integrate the connectors in a novel way, and all these details are new details. I mean, we're thinking of the geometry, we're thinking of the way that we connect these parts, and we are basically in charge of all these bespoke connection details. You can see here the way that the large-scale chandelier is integrated, and we didn't want to make just a number of objects here. We wanted to create a space. We wanted to create a space that could be, the space itself could inspire the people that goes in, and could inspire as well the employees. We structured the space in 3 bands. The one on the left is the red, more didactic band. The one in the center is the action. The white on the side is more for the high table and having some views. And then we developed the whole concept for them. And the red wall was the red wall for basically to learn from these processes. So we made all these drawings and the explanations so people can look at the process and actually enjoy kind of the space, learning something. You can see here images of that space. We work, of course, at the small scale with the furniture, with the chairs, tweaking IKEA lamps as well. So we had a lot of fun with our students, with researchers, working at different scales. And we involved the employees here. So the DB Schenker employees were the ones assembling the chandeliers. So we ran seminars and workshops for them to learn how to put them together. And that was the process that we follow with them. So this is how the space looks. In the end, there's a number of chandeliers, 5 chandeliers, the red wall, and then we have basically turned this lunchroom space into kind of a space that can transfer and somehow show the values of what is possible to be done with waste. This is us working with them, integrating details for the lights. And it has been one of the first spaces in Singapore that was actually integrating these components in a functional way. And then we continue our journey as well in our own campus. So the idea was, can we scale it to maybe 150 square meter surface that could be made of 3D printed tiles that can create relatively complex geometries or smooth geometries out of the tiles. So this is the main space for our university, the main campus. So we had the opportunity to create an iconic piece for the 10th anniversary of the beginning of our school. And then in the central part, we designed this kind of wave that creates pockets of spaces towards the outside, and inside becomes a bit more immersive. And then we have a space inside. And the idea was to create a system whereby we can design those tiles with all the connections and references that allows us to create that shape, and also print it in a farm of printers created by our students. The idea was to get every student with a printer to be able to contribute to making this surface. The idea was to create a relatively large-scale structure that meets the CNC routes waffle structure below. And that was done, actually, designed and manufactured in about 3 months. From conception to implementation. It was a really quick design exercise that involved many people. And, well, it was a bit of quite complex to address. I mean, in the end, we have about 3,500 tiles. So we had to print kind of templates for the students to know where to put them. But it's quite impressive, the way that it turned out in such little time. We designed details like for the edge, integrating elements that rigidize, integrating metal parts, to make them strong. And this is how the materiality looks like, allowing people to step in. The central part actually is CNC in woods and blends with the tiles seamlessly. This is the space from the outside. So these pockets, this kind of became a central stage for that space. So just by bending, you create these 4 pockets of spaces, but also people can go inside. There was a very simple geometry, and it turned out quite well. Well, we look at plastic as a problem, and we keep working on this process of using PETG to, in this case, to produce a floating farm. As part of our research with Netatech and NAMIC, we started working on a station. It's a quite domestic station that we started working with to turn the plastic bottles into filament, and with that filament and pellets, we were able to produce these kind of floating farms. So the idea was to create smaller pots instead of bigger ones. That the idea is to avoid blocking the light, and we can deploy them in the water bodies of Singapore, and then produce some food, right? Also, they could contribute to something that could be nice to look at, and it could be in different water reservoirs. We optimize the space for the crops, and then we explore different strategies for the ventilation. Here, the challenge is, of course, the sunlight that goes inside, but also the ventilation. We explored 3 different options for the mechanical ventilation or the natural ventilation, and we opted for this one. So that's the resulting shape. Turned out like this, a bit like odd, but we developed some simulations and the airflow, and we thought that this was going to work okay. And this is how it looks from below. This basically consists of 2 parts. One is the platform. The top is the cupola. And we did like a first 3D printed prototype. That was the first version. The second version was to use, because we wanted to test the UV light that goes to the plants, we made a first shell. So we produced a 1:2, 1:3 prototype, printed in our lab, put it together with our epoxy, and just makeshift, but worked. So we deployed it out, and we just put it in the pond. It was working okay, as expected. And then we moved into the 1:1 prototype. For the 1:1 prototype, we had to strengthen the structure, because we had to get a very thin layer, so we get more than 70% of the UV light inside, but at the same time, it's to be stable. So we work with the lattice structure to go. We did run a number of iterations with the equipment that we had. We were using for this one the big rep that we are all familiar with. We know it very well, like the pros and cons, but I mean, it's a machine that was able to print the volume of 1 by 1 by 1 for us. And we explored different patterns. These are different versions. And then the 1:1 version was achieved. This is how it looks. We put the solar panel on top, and then we had our fan. So we get the ventilation achieved, and it was deployed into the water pond, and yeah, it was working quite okay. So it's a cute piece. I think this is version 1. We are working on version 2 with the same company, and we expect to have some number of units deployed in Singapore as an example of things that you can do with waste, and in this case with PET plastic waste. Concerning waste, we are working with Chanel, and we started working with them to find ideas to upcycle what they have, what they throw. We know they throw a lot of things. So the idea here was to design a device that could be locally manufactured, locally printed, and it would be easy to reproduce anywhere. So the idea was to create a device that can integrate the Chanel bottles that they throw after the events or they have discarded from the stores, and we can create chandeliers out of that, and that could be implemented in any store locally. So it's made of a piece that actually is integrated by a number of sectors together, connected internally, and then we got upcycled aluminum bars to integrate the new caps and the bottles with the core. We have 2 options here. Is the one standing, and the other one is like suspended. So the one we have here is the one that we did for the warehouse, and they are actually quite happy. So hopefully we can move forward with the implementation on the stores in the coming year. But one of the motivations that we have in the lab goes beyond maybe the creation of those forms, and we are looking at additive manufacture on performance and expressivity in space frame structures. So we believe that this way to go as reduce the wastage, as also creates, for us as designers, give us a radical new aesthetics as a result of the process, as a result of the thinking, and also, of course, can unlock free-form design for real. And we're looking at space frame structures at the poly that for us is very interesting, very important. It's very attractive to us from the beginning, and we thought that was a really good use case of application of 3D printing. We're familiarized with the standardized space frame nodes, the mirror systems, that still is kind of quite dominant in this industry. We had the vision to start integrating 3D printing connections to solve the intersection of the bars, so we can unlock freeform, we can solve the geometric discontinuity between parts. The idea was to make it seamless, and also to basically to get kind of a certain learnedness and optimization of the structure that other methods wouldn't allow. It was inspired by a neural network. Our nodes are the ones that are printed, and the bars are going to be standard. That was a clear direction we wanted to print just what is needed here, and then to integrate what is standardized and keep doing that. And definitely inspired by then it was 2009. So we have these examples of amazing optimization of the node design. But we wanted to give a different take to it. So we start testing the idea at different scales and with different functions. So here I'm gonna present 5 designs. This is the open house pavilion. This is the I Like Marina Bay pavilion. This is the Sombra Verde. Here we have the air table and also the air mesh pavilion. These 5 projects help us test the idea with different materials, with different functions, in different contexts, indoor, outdoor, different scales. So we wanted to develop, and not only at one scale or just only serving one function. We were evolving the idea and testing it, learning from that. The first one is the V-Mesh project. It was the seed, the beginning of our journey on working on space frame structures. And here I'm gonna show maybe the original drawings with the 3D models that we used then. You can see the number of parts. It's very important, as you know, controlling the data that you're working with, the nodes, the bars, and all the different elements of the system. So to generate the nodes, to generate the geometry in which the bars converge to the center, we created a simple Grasshopper script. This is the version 0.1, if you may, but it's the most easy to understand. So you can see here we have the lines, then we have the nodes, and then we go to the bars. We do a fast iteration where we get the vector stream to a certain scale, a certain length that we define. So we have just a diagrammatic approach of the lines, and then we subtract the lines to the bars. Then we start looking at the geometry in a simple way, and also give us the estimated cost in a rough way at the beginning. We can get the surface that we're gonna print, and typically it's quite accurate, quite on point. So in 3D, we look at the node in a more detailed way. We have the bars in 3D bars. And then this is the geometry that we create. It's only creating polygons and convex hull geometry. So what we do is to remove the space for the bars that are defined by 4 points. And then what we do is to create a convex hull that can connect the bars. That gives us a geometry of a very low resolution that when it's smoothed out, creates a very nice transition between bar and nodes. And that can be automated very quickly. And we basically have the connection on the ends and the reference of the numbers and bounding box. Then we orient it in the right direction. And there we go. We have the nodes. So that's the node. It's hollowed, as you can see here. And then we immediately get kind of the range of the nodes, and we can estimate the cost of the pavilion at the beginning, right? We have basically the rates of what is going to be the cost. We can sort them, we can analyze. And then here is important because the geometry itself, if we move a vertex, maybe the branches are going to be narrower or wider, and that determines the shape and that also determines the cost. Sometimes just moving vertices here and there can reduce the cost, of course. There are other factors involved, but then we can see how we can reduce the size of the nodes by modifying the geometry. This is the first set of nodes that we created using PA12 and binder jetting, stainless steel, and bronze alloy by then. That's a 4060. And this is the PA nodes. And this is this alloy of bronze and stainless steel. So we had two kinds to test. I was started putting it together. And yeah, we were quite happy with the slenderness. It was actually extremely thin, the diameter, and the connection came out quite well. You can see here the implementation on the site. And it served as the open house pavilion in 2017. And we had a simple exhibition running through a few weeks. You can see how the nodes were connected in space, and basically the slenderness and the lightness was there. We were quite happy of the performance of the structure. Became kind of this kind of canopy on the central space of the campus. And then the next iteration was to integrate services inside. So since we have the space, since we have an empty space inside the nodes, can we run electronics? Can we run circuits? Can we run water? So the structure could be actually used in a different way. So then we conceived these nodes for a pavilion at the Marina Bay in Singapore, where we're integrating not just the structural component, but also there's electronics inside. There's LEDs running through that they will be orchestrated in 3D. And then we created, of course, a 3D model to start working on the optimization of the position of the vertices. 147 nodes were created here with this crystalline geometry, more faceted, and was extremely challenging for us working with 54 circuits running three-dimensionally in this structure, because we are addressing in total 32,000 LEDs through this structure, especially. So it was a really complex code for us to solve. The structure was developed in our lab, and then we took it to the site, but then we had to work on site. So electronics involved was actually very challenging, but we managed to put it together. And this is the result, where people could interact with the piece, and actually the light was reacting to their presence. And this is the look. We have the light inside, and the materiality of the structure was actually very different to any other structure. It can actually react, and the colors and the lightness was perceived by people. You can see also the kind of how people could interact with touch. And then at some point we wanted to test the structural limits of this. So we are in charge of the calculation, but we wanted to see the limits of this physical construction. So we were actually trying to make it collapse. So 3 of us were in the end able to make one of the longest bar buckle, and then the structure fell down, and of course we destroyed the pavilion. We're very used to that, right? We make something, only is a one-off, and then what do we do with the waste, right? So in our case, we wanted to give it a second life. So we turned the pavilion into a chandelier. So in the National Design Center, we collected all the bars as possible, the ones that were not broken, and then we printed a new detail for the light bulbs, and then we created light shining in. And that's the feature of the National Design Center chandelier, out of basically the waste that we made of the pavilion at Marina Bay. So the idea was to extend the cycle and continue the design with a different function and a different context. So the chandelier, we put it low so actually people can touch it, and at some point you can put it high so it becomes a nice feature for the space. Also, we wanted to test the idea with different materials. So in this case, we work with bamboo. So since we are in a tropical context in Singapore, it's a relevant material for construction. Can we use bamboo as a renewable, fast-growing, and powerful carbon sink? The idea was to work with bamboo in a different way than bundling or connecting bamboos in a traditional way. Can we use 3D printing here as well? And the problem is that all bamboo poles are different. So it's difficult to integrate something that is not regular. So we found the solution just working with a very low-tech scanner, like a 2D scanner. So we cut the bamboo poles to a certain length, and then we register the sections immediately with a script. So what we get is all the scans directly into a database, the two ends of each bamboo pole, and that is streamlined from bitmap to vector, and vector to a 3D printer connector. The idea is that we have that flow that basically when we scan is registered and transferred already to a STL file that we can print with a reference. The result is that the piece actually fits perfectly to the shape of the bamboo. And then we are able to confidently go ahead with this node system that we tested before. And for here, we use a bit of bigger printers, but still, in this case, working with PLA of a piece that could be about like 40 by 40 or 30 by 40 cm. So it's relatively big. And each of them probably took about like 5 to 8 days or 9 days to be printed, each piece. We were working with 10 centimeters, 10 millimeters thickness. We developed the system to connect, integrating steel cables instead of some of the bars that were actually running in tension. So we developed a number of components. We did some tensile tests too, so we were confident to go ahead with the solution. And then we started assembling that in the lab, and then we took it to the site. The geometry for this pavilion, we relied again in a tetrahedral topology. So we work with tetrahedrons as the base, and then we adjusted to the site. It started with a regular geometry, and then we moved into a more adjusted geometry, and it's in the kind of these quite nice alleys that we have in Singapore, in back of the shop houses. And then we put it together with our team of researchers and students. To put the canopy together was about like 3 hours. Then mounting the roof took a bit longer. But the detail of the roof was very simple. As you can see here, just a peg on top, and then we have a polycarbonate roof, simple and inexpensive for our budget. But we were able to extend kind of the geometry of the bamboo and the tectonic somehow, and the roughness as well, if you may, through these connectors. And we felt that this was kind of a natural way to extend the material. We're working here with PLA, biopolymer materials. So that was the intent to create a structure that could be easy to assemble. And as a result, we thought of a system that could be actually very easy to put together for affordable structures. And we work with the Archifest and Dynamic team to put it together as a display on an exhibition. And we worked as well with bamboo and the idea of the nodes, but in this case, stretching the node longitudinally. So we have, instead of a node, we have a trout. So we can create a frame with bamboo poles in which in this case, the bamboo poles are crossed in space, and then the nodes are longer. So with that strategy, we can create a lattice. So that lattice, which is a simple system and very easy to assemble, allows, we work with the farmers to dimension what is the optimal size for them, and we work on integrating the pipes inside of the bamboo pole, so actually runs inside of the bamboo, and then we have at the end solar cell to pump the water, and this is kind of the result. We have a device that we can install in parks, we can install in any space of social housing in Singapore. People can maintain and can adopt different forms. It can be actually this design, but we can of course adjust the geometry to increase the height or to create smoother geometry to adapt to a different condition. So this was the prototype that we built for the Singapore Academy. And we went back to maybe high performance materials like steel. And then here we tested the idea at a smaller scale. So here we're looking at the air table. We wanted to go to use stainless steel as the material to work. And the idea was to optimize the geometry and to use a table as a proxy to test that structure. So we wanted to put 200 kilos into 3 points. And the idea was to transfer using a space frame, using 6 millimeter in diameter for the bars. So we run some optimizations. We create the geometry, the 3-dimensional model, the one you can see here. And basically you can see the design of the table where all the components are integrated. After optimization, this is the geometry, which is radially symmetric. So we have, for the 3 legs, actually we have still as well as symmetry here. So we are reducing the number of different nodes. It's a design choice. And then we start working with the prototype. You can see here the bars are extremely thin. We're working at 6 millimeter in diameter. They're connected using a threaded connection. So we're actually threading in and out. The assembly sequence was crucial for us because we were going to a point in which was very difficult to put the bars together. There's no space. And because we use this strategy, we use the threads, right hand and left hand. So the bar, the nodes and bar, when you are threading one bar, the nodes come together. So theoretically it worked really well. At some point, you have the redundancy of the bars make it difficult to close, right? We have also space. And with this case, it's not like the plastic bars we had before. This is difficult to bend. So we learned from the process that if we want to scale this system, it's difficult to work with this detail for sure. But we were able to troubleshoot and finish the table, and the performance of the table was quite impressive. We are, using less than 15 kilos of structure, and we're supporting more than 200. And the load transfer goes to this like very minute, like small, 3 points, like it's more than a coin, and it tells about the precision and the way that we are able to transfer the loads. It was very, very stable, and we work on the details, the connection with the table. You can see here the close-ups, the connection between some of the bars. You can see it's not fully, tangent because of that problem that I mentioned, but most of the bars were actually looking quite good, and the connection was quite precise. Here you can see the details, the close-ups of the nodes and the bars at that small scale, right? And then it turned out quite okay. In the meantime, we're working on a different project for table as well, testing using a bit like kind of AI to optimize the simulations for the force analysis. The idea was to test the flow forces and to transfer that into a geometry. So for the table leg in this case, we're working with a geometry that was driven by the forces themselves, and we work with voxel jet to work on the creation of the ceramic molds to use to create these kind of bronze legs that are manufactured with this complexity. So the geometry is basically what we got from the optimization process. So those elements are force driven, and this was we're here trying to explore the aesthetics resulting from the process. We work with the bronze, we polish it. We have the 3 different legs as we put the table with a non-symmetric condition. And this is kind of the result that we got. We got to learn a lot with the process. We work with voxel jet to manufacture the legs actually here in Germany, and the result was quite good. It's kind of the first time we work with this technology ourselves, and voxel jet actually was very keen on working with us and develop their technology to create this part. So this is the furniture that we made with the 3 legs integrated. It was done also during, I think, COVID time, so it was actually hard to progress in the prototyping, but we made it to work. You can see here the quality, and the underneath also is made in bronze, so we made the detail flush. And then we wanted to take it to a code compliant, standardized, standard like the Euro code that we have in Singapore. And the idea was to use the system in a real place, like people can actually use. So we selected Gardens by the Bay to work with them. And they were very excited to be maybe the first to integrate a 3D printed stainless steel structure in a functional way. So we chose a small plot that they had vacant. It's just a green patch. It's actually not a very visited space in the gardens, but we found that was actually a quite nice spot where we had this point here. We have some reference points to the context, to different buildings that that are quite iconic there. This is a pavilion done by Thomas Schreffer. It's the SG50 dome, and there's other vantage points that are nice to capture. So our device, our floor plan was driven by the vectors of the views. So we created that pavilion there and the top of that green plane. And the idea was to create a bit of like that kind of like edge condition where you can look at somewhere. And we wanted to test some ideas here. We wanted to test maybe a cantilever, a ramp, an entrance. We wanted to explore some architectural features in this pavilion. So the geometry also created with tetrahedrons. You can see the unit of a tetrahedron here, the nodes, the bars, and then we work with the double skin principle, basically towards the edges, converges to thickness 0, and then opens up to get the depth to be able to withstand the loads. This is the idea for the geometry. And we work with Eurocode standards to meet the regulations in Singapore. It was actually quite challenging because they didn't use stainless steel before 3D printed in any of the construction. So it was very, very difficult to get it approved. So we had to run a lot of simulations, a number of detailed tests for them to be able to approve the construction to be open to public. So, well, we calculated it, we estimated the reactions, we basically adjusted the geometry. You can see here the size, the scale, something that people could enter, could lean, could sit down, could look at, could touch, something that could be accessible to everyone. And to generate the geometry, as mentioned, we work with this tetrahedral typology that allows us to optimize the structure, modifying the vertices. The nodes are generated with a more developed algorithm from the one that I showed at the beginning. The loads are determining the sizes of the bars. This is the way that the nodes are going to look like. And the generation entails a number of steps here. So, of course, we assign a certain diameter. We start working with, you can see here in number 4 is the convex hull structure, right? It's like basically a very low-res geometry, but it's consistent when we are applying it to the bars. Give us the nice tangent in a very simple manner. That's why, for us, convex hull has been kind of the way to go at the beginning of the geometry. Then we go with the section. We apply the thickness of a different thickness at the beginning. We go also for the connection system, the threaded connections, but in this case, the threaded is part of the node. We directly go for printing that we know is much better in comparison to standard nodes if we made it with traditional material, with traditional methods. But the most important thing here as well is that we are actually saving a lot of material compared to a solid node is 80% air inside. So it's actually very light. So we're printing a shell in the end. This is one of the nodes with all the systems integrated. And basically what we have is a system that allows us to almost real time adjust to the loads that we have and to the geometry that we have. So it is very fast. I mean, we're working with a script that basically takes only a few steps to create the geometry and a few more steps to design every single node and every single part involved in this components. So this is the first node that we printed. So it integrates standard bolts from M8 to M20, and the thread is also printed and calibrated, so we can directly integrate that standard components in. A total of 54 nodes were designed, where we were working with different details as well. So these selected here are the ones that are going to hold the frames, so they're flat on one end. So we implemented that in our script. You can select that some nodes are going to hold the panel, so they will cut that part of the branch and they will integrate a different detail. So we started looking at more specialized nodes. It's not only just purely structure, but also we have the foundations here. So the foundations also integrate a special, bolt to be connected to the foundation plate. And then this is basically the spectrum of the nodes. We have the weight, we have the dimensions, so we know everything about it. And then we print them and we code them in white, in this case, a selection that we had for the pavilion. We label them, and the labels in this particular project, we use a temporary label. So we print them, we use a color code to know the areas in which we're working, so it's easier to access the components. So we label them all, And then, well, this is basically the details that we are using here for our system. So this is the prototyping phase. Before we went to the final production, we used PA12 as the selection of material for testing. So we calibrated different bars with different diameters and different lengths to be able to optimize the diameter of the bars as much as we could. So we have 5 different types of bars. So according to the structure, we assign them. So most of them are of the thinnest diameter. Tensile tests were done, and majority of the cases, the bar was actually breaking and the node was actually intact. So that was very convincing, when it came to get the approval. Like, most of the samples actually broke on the bar and not on the node. We also ran FEM for all the nodes. So they had information of all the nodes when we submitted the calculations. And we did our, geometric prototypes to understand length, understand, how easy was the system to be, implemented on site. This is just a simple prototype to see how we're gonna connect them. We also used kind of a simple design for the caps. So the idea was to get them covered and continuous. So in the end, we can make it flash. And then we went to the assembly of the final prototype. We started printing the nodes, prototyping PA12. We tested the threads. The connection of them was actually quite, smooth of, the threads and the nodes. We started to put them together and to create this kind of 3-dimensional complex structure. This is the first version on the left, PA12. The right, you can see the nodes that we used by then is a stainless steel with it's a mix. It's not fully 100% the steel that we can print now, the 316L. So it was what we had then on our range, and but the performance was really, really good. The property that we couldn't meet was the elongation. Elongation was still like not meeting the standards, but was enough for 3 years approval. And well, we made the assembly first in our campus, a team of, I think it's like 6 people in total, using just simple, tools and ladders. So the idea, the feeling was like we're creating a very high performance structure using our, normal tools, like feels like IKEA, but in stainless steel, right? So the system was very, very easy to put together. So that take basically 2 days of work. And then we 3D scanned the structure to see if any deviation. So we went to the site and started working on the assembly. Again, here we only got a construction company to help us with the foundation, because they wanted to have a foundation for it. We wanted just to have small ones, but Gardens by the Bay was very strict with that. So we let them do the foundations. This is the final geometry of the different parts, the deck, the details that we had to support the deck. And this is the foundation that we had. And then this is the plates. The nodes are are connecting the plates, the standard plates in a very precise way. And this is how we are going to connect the nodes and the bars. 5 minutes. 2 minutes. So I will be fast here. Just the way that we connect the bars. I'm gonna run through a bit like the images that shows the complexity of the structure, and we wrap it with a upcycle fishing net. So that was the material that we chose for the cladding. 2 layers of that. The fishing net wrap took almost a week. So it was actually 10 times longer than putting together the structure. The structure was just a day. So that's, we did the load test. We started working on the deflection. The VCA people was there, witnessing that barely moved. So it was there, quite solid. And we were very happy about the outcome because, it was the first time that there was something like that built in Singapore. And for us was an achievement that we were able to go around the code and somehow be able to have it there, open to people. So there's me, my wife, and my kid. This is how the structure looked at night. We put some LEDs so people could take some Instagram pictures. And this is how, we found people going there just to see the environment. So it was like something found, very light, very, we don't know what's that, right? It's like and then we got the PDA in Singapore. So then we started working with the government, and that led us to new exciting opportunities that I hope I can share in the coming years on residential structures. It's really good for extension when you cannot access with with your trucks and your lorries. You can actually go deploy and extend your house. So we have this project ongoing. So hopefully we can show the final the documents submitted. So it's gonna be approved. And 2 small experiences that will take me 1 minute. This is the COP28 Dubai that we did the pavilion for the Singapore pavilion, for the United Nations pavilion. So we basically displayed the technology, and it was really good because ministers and authorities were actually quite happy about the performance, the system, the easiness of it, and we're moving forward to take it to a larger scale. So that was the last year's pavilion, integrating waste and 3D printed nodes into one piece. And the last one I just finished, and the pictures are from like the team that was there in Beijing. We created this cube structure using a very simple system of nodes and PLA and then recycled acrylic bars and PA12 nodes to create a relatively lightweight and complex network of cubes that is self-supporting. So with no additional structure, we used the diagonals. We put them to reinforce the structure what was needed, and became a quite iconic space for this festival. And you can see here the details and connections. So, well, that's the last slide. Thank you very much for your presence here. And you want to know more, we have this 3D printed architecture book. But if you want to know way more, we can talk, and then we can discuss maybe over a drink or coffee after the talk. Thank you very much.